In section 7.6, we do something very interesting. We take the Lewis structures that we've been developing for covalent molecules and we apply a very simple theory called VSEPR theory, and that's going to allow us to determine the geometry of our atoms in three-dimensional space. So I've broken this section into three parts, and in the first part we're going to look at the basics of VSEPR theory and how that's related to electron group geometry. So what we've been concerned with to date is how electrons are distributed between the different atoms that make up a molecule or perhaps a polyatomic ion. So we've really been looking at how are electrons shared between atoms, or alternatively how are electrons transferred between atoms. What we're going to do now is consider how the atoms themselves are organized in three-dimensional space, and this is like really important. If you consider something like a protein, and this is an example, this example protein here is one called nitrogenase. It's the three-dimensional arrangement of the atoms in this protein that give rise to what we call the binding site, and in this case the active site, the site where the molecule of interest binds in this proton, is this thing called the iron molybdenum cofactor. The three-dimensional structure of that is what determines the reactivity of this molecule, and it can have a profound effect. So the nitrogenase protein takes nitrogen gas and it adds to it protons and electrons, and it forms ammonia and hydrogen. Now, conventionally, when humans attempt to do this reaction in the absence of the nitrogenase protein, we require very high energies, and in fact it's estimated something like about 5% of all global energy is used performing this reaction artificially. Now, the nitrogenase protein, guess what? It does this reaction at room temperature, using very small amounts of energy. It does it effortlessly, and it all comes down to the very precise arrangement of atoms in the iron molybdenum cofactor. So what Lewis structures describe is how atoms are connected to one another and how electrons are being shared. And the majority of the time, these Lewis structures are not actually related to the three-dimensional shape of our molecules. So carbon dioxide has this Lewis structure, where we have three atoms, two oxygen atoms, that are the outer atoms and a central carbon atom. And we tend to draw it like this, where all of the atoms are in a line. And it actually turns out that that is the correct three-dimensional structure of the molecule. So yes, indeed, they are all lined up in a straight line. But you could imagine that they could also be in a bent kind of shape. And the Lewis structure isn't able to tell us, will this molecule be linear, like the ball and stick model that is shown, or whether it will be bent. Now, when we draw the Lewis structure for methane, we tend to draw it like this, where we put 90-degree bond angles between the hydrogen-carbon hydrogens there. But in reality, and we also kind of tend to indicate that it's flat. In reality, it is not flat, it's three-dimensional, and the bond angle, the hydrogen-carbon-hydrogen bond angle, is nowhere near 90 degrees, it's actually 109.5. So the Lewis structures are not intended to indicate the shapes of the molecules, they're just intended to tell you how electrons are being shared. So the simplest model, and the first model that we're going to consider that can help us understand molecular shape, is called the valence shell electron pair repulsion theory, or what we call VSEPR theory. And it's a very simple idea. It recognizes that electrons are negatively charged, and things with the same charge tend to repel one another and keep out of each other's way. So the VSEPR theory is quite simple. It says each group of electrons around a central atom is located as far away from each other group of electrons as possible in order to minimize repulsions. So it's a pretty simple idea. If you have a group of electrons around a central atom, those different groups are just going to kind of position themselves geometrically to maximize their distance between each other. So what do we mean by an electron group or a group of electrons? We mean either a lone pair of electrons or a bond of any type. It doesn't matter whether it's a single, double, or triple, that's one electron group. So if I look at carbon dioxide, what I have to, and I want to figure out the number of electron groups, what I have to do is begin with an accurate Lewis structure. So here it is here, the carbon is connected to the oxygen via double bonds. And so do we have any lone electron pairs on the carbon atom? There are 0 of those. How many bonds do we have? 1, 2. So this molecule has 2 electron groups around the central carbon atom. So let's go ahead and do some more. This is the Lewis structure for ammonia. You start to memorize some of these after a while. So how many electron groups? Well, it's got the 1 lone pair, and then we've got 1, 2, 3 bonds. So that gives me a total of 4 electron groups. Okay. If I go to SO2 and I go through and I draw a Lewis diagram for it, the best Lewis diagram for it, it ends up being like this. Turns out that this molecule has an expanded octet. So I've got 1 lone pair and I've got 2 bonds. Keep in mind you don't count the double bonds twice, so it's got 3 electron groups. If I draw the Lewis structure for the water molecule, I end up with a structure like so. It's got 2 lone pairs, and there are 2 bonds there, 1, 2. So it has a total of 4 electron groups. Okay. So why is it important to know the number of electron groups? Because it's the number of electron groups around a central atom that are going to determine the shape of our molecule. So this number of electron groups is referred to as the steric number. So it's pretty simple. It's the number of atoms bonded to the central atom plus the number of lone pairs on the central atom, and that gives you this thing called the steric number. And you know, it can go, we're going to see examples where the steric number goes as high as like 8. Or actually, we're only going to go up to 6, but it can go higher. We're actually going to go to 6. So methane, number of atoms bonded to the central atom, 1, 2, 3, 4. No lone pairs, steric number 4. Now, the VCPR theory said that every group of electrons around a central atom is located as far away from each other group as possible to minimize repulsions. So we're going to look at central atoms that have 2 electron groups, 3 electron groups, all the way up to 6 electron groups. And think about how you can organize these groups so that they put the maximum distance between each other. So when we have 2 electron groups, the best way of organizing those 2 electron groups to keep the maximum distance between each other is in what we call a linear fashion with 180 degrees between the 2 groups. When we have 3 electron groups, the best way of organizing them so that they can keep out of each other's way is in an arrangement called the trigonal planar arrangement. This is flat, and we have the 3 electron groups are pointed towards the corners of an equilateral triangle with a bond angle of 120 degrees between them. When we have 4 electron groups, this I should point out is 2 electron groups. When we have 4 electron groups, we will have the tetrahedral electron group geometry, where we have the atoms or the electron groups are directed towards the corners of a triangular based pyramid with the central atom in the middle of that pyramid, so it's 3-dimensional, not planar, and then the bond angle between those electron groups is now 109 degrees. So that's for 4 electron groups. We'll look at this, why we are drawing some of these things in shapes other than lines a little later on. When we have 5 electron groups, those electron groups are going to be organized in what we call the trigonal bipyramid arrangement. We have our central atom with 1 electron group directed above it, 1 electron group directed below it with 180 degrees between them. And then at 90 degrees, all in a plane, sort of bisecting the angle between those 2 electron groups, is a set of 3 electron groups, all in the same plane, that have a 120 degree angle between them. And again, I'll have to go through this in a little more detail later. When we have 6 electron groups, which is the biggest one that we're going to be considering, we have the octahedral arrangement of electron groups. We have our central atom, we've got 1 atom above it, 1 atom below it, and then there is a plane of electron groups sort of that bisect those 2 and contain the central atom, and those electron groups all have 90 degrees between each other. And again, I'm going to have to kind of explain what this looks like to you a little later on. So yeah, it's kind of an interesting sort of setup. And we also need to explain why we're putting these dashes and why we're putting these wedges, and we will get there. So we have 1, 2, 3, 4, 5 electron group geometries that you need to know the names of and the angles between those electron groups in those particular categories. So now we go through some sort of detailed description of examples of molecules from each class. So an example of a molecule where the central atom has steric number equals 2 is CO2, which we looked at before. And sure enough, as predicted by the VSEPR theory, the bond angle is 180 degrees. We call this electron group geometry linear. Okay. Now, it's interesting to talk about electron group geometries, but we're also going to be talking about what we call molecular geometries. Molecular geometries are just focusing on where the atoms are in the molecule, and we ignore the presence of lone pairs. So we're just going to be, when we're talking about a molecular geometry, we're just going to be focusing on where the atoms are. And the important thing to recognize is that the electron group geometry and the molecular geometry will be identical when you don't have any lone pairs on your central atom. So we don't want to get too bogged down in that distinction for CO2. When we go to steric number equals 3, we have the trigonal planar electron group geometry, and that's going to have an ideal bond angle of 120 degrees. So a good example of this is the electron deficient molecule that we talked about earlier, boron trifluoride. And so the angle in here is 120 degrees, and this molecule is flat. It has the trigonal planar arrangement. Now, if you don't have any double bonds here, you're going to have an electron deficient molecule. More common is to have a trigonal planar molecules that do have a complete octet by forming a double bond to one of the atoms, and a good example of that is the nitrate anion. So here we have nitrate, it's got 1 double bond in here, but we've got 1, 2, 3 attached atoms, so steric number equals 3. This is also going to be trigonal planar, it's going to be flat, and it's going to have a bond angle in there of 120 degrees. Here's another one. This is called formaldehyde, CH2O. Here's the Lewis diagram. We've got 1, 2, 3. Steric number equals 3. It's going to be trigonal planar. The bond angle is going to be about 120 degrees. Now, in this example, I've pointed out that the bond angle is not quite 120 degrees. I'm going to draw it kind of like over here. and kind of illustrate what's going on. There are 4 electrons in the double bond, which means that they are more effective at repelling electron pairs than single bonds. So what happens is that these guys push on those a little bit, and that causes this to squish up and that to expand. So whenever we have a double bond, we're always going to see this kind of deviation from ideality, because double bonds are more repulsive than single bonds. So there are questions where you're going to be asked to comment on the deviation from the ideal bond angle, and often it is due to a double bond. Okay. When we move to steric number equals 4, we're going to have what we call the tetrahedral arrangement. And a good example of this is methane. Now, the tetrahedral arrangement is the first time that we see that we've moved from having flat molecules to having three-dimensional molecules. And we generally indicate the three-dimensionality of a molecule using what we call dashes and wedges. So in the dash and wedge kind of notation, lines indicate that a bond is in the plane of a page, dashes indicate that the bond is behind the page, and wedges indicate that it's coming out of the page and is in front of the page. So these guys are kind of flat in the plane of the page, and then this one is going behind, and then this one is coming out at you. So the tetrahedral arrangement is the electron groups are directed towards the corners of a triangular-based pyramid, and the central atom is in the very middle of that pyramid. It looks a little like a D4 if you've ever played games where you have to roll different shaped dice. In the tetrahedral arrangement, the bond angle is 109.5 degrees. When we go to steric number 5, steric number equals 5, our molecule or ion will have what we call the trigonal bipyramidal electron group geometry. So a good example of that is PCl5. So here's our central phosphorus atom. We have one of our chlorines is below the phosphorus atom, one is above, and then around what we call like the waist of the molecule, we have these 3 chlorine atoms that are all in the same plane. They're in a trigonal planar arrangement. So we have this sort of triangle of atoms in the middle, and then we've got one above and one below. Okay, so you're only ever going to see this when your central atom has an expanded valence shell, that is, it belongs to period 3 or beyond, because if you count up the electrons around that central atom, you've got 2, 4, 6, 8, 10. So for trigonal bipyramidal, you can see there are really 2 types of atoms. There's these guys that are above and below the central plane, and then there are these guys that make up that central plane. So these are broken into 2 categories. We talk about the ones that lie around the middle in a trigonal planar arrangement with 120 degrees between them. They're referred to as the equatorial electron groups. And then this second set that are above and below the equatorial group, they're referred to as the axial set of electron groups, and there are 180 degrees between each other and 90 degrees between them and the equatorial set of electron groups. So you need to kind of know what people are talking about when they're talking about the axial and equatorial positions. And again, they're using the lines, dashes, and wedges to indicate whether the electron group is in the plane, behind the plane, or in front of the plane. Okay. The last class of molecules we're going to look at are those that have steric number equals 6, and steric number equals 6 gives rise to the octahedral electron group geometry. A good example of this is sulfur hexafluoride. Again, you're only going to be seeing a central atom with 6 things attached to it when you have an expanded valence shell, so your atom comes from period 3 or beyond. So the octahedral electron group geometry is kind of similar to trigonal bipyramid. You have your central atom here, and then we've got one above, one below, and they form an axial set of electron groups. And then this time we've got 4 atoms around the waist of the molecule at 90 degrees to the axial pair. But these guys, they have 90 degrees between them rather than 120. So they are in what we call a square planar arrangement. They're all in the same plane, but those electron groups are directed towards the corners of a square. Again, we can talk for the octahedral arrangement, we can talk about equatorial electron groups and axial electron groups. So the equatorial electron groups are all in the same plane. There is 90 degrees between them, and they are directed towards the corners of a square. This is referred to as a square planar arrangement. Above and below that square planar arrangement, we have the axial electron groups, and they have 90 degrees between the equatorial set and 180 degrees between each other. So all of the bond angles in the octahedral arrangement are 90 degrees. Okay, so that gets us to the end of the first section that I wanted to talk about, which was just the basics of VSEPR theory and how we have these 5 different electron group geometries.